but also increasingly deployments into industry and commercial settings. So we have two primary projects that we steward. One is the ROS, the Robot Operating System, and the second is Gazebo, which is a physics-based simulator that can simulate sensors and actuators. And I'll talk more about these two projects and how they interact. Before I get any further, though, I should note that when we use the word operating system, it's in a bit of a different context and a different intention than oftentimes it's done. So we oftentimes think of operating systems as abstractions that sit on top of common hardware, like a file system or a graphics driver or a network encapsulation. And that's great. And it's been around for many decades. It's a fantastic level of abstraction. But oftentimes in robotics, we actually want to go one level higher than that. Because, for example, many robots, if not most robots nowadays, have more than one computer on them. So you need to be operating between multiple machines, as well as providing the next level of abstraction for things like sensors and actuators so that we can operate at a higher level with both the hardware as well as the descriptions of the robot and its physical strength, structures, and how it interacts with the world around it. So like many open source groups, we're supported by a generous collection of sponsors, including many government agencies, as well as large corporations and individual contributors as well, from a financial standpoint. And then we get many, many, many contributions, like all open source projects do, from all over the world, from many thousands of people, and we're very grateful for that. So if we back up a little bit and let's think about what a robot looks like, it's, coming from the computer science perspective, you can look at it as it's a bunch of software that has to receive data from sensors, a bank of sensors, has to make some sort of decision or modeling about that sensor data, and then reach down back through the world through a collection of actuators. And in the meantime, while we're doing all that stuff, the world itself is reacting. And in fact, our actuators may be effects in the world, but then we're gonna see a response from the sensors. So there's a big loop there that needs to be closed using software. And what we're seeing over time is that the complexity of that software keeps increasing as people are trying to do more and more things with their robots. So what we're trying to do to attack it is, rather than try to end up with these monolithic software blobs, instead break it up into many different smaller pieces. The goal of that is there are lots of pieces that we're trying to do, but one of the primary things is to achieve reusability. So that when you have a submodule that's a device driver for a particular robot, or maybe a path planner, or some other part of the robot functionality, once that's debugged and working, in theory, you should be able to apply that to lots of different applications. And I'll show some videos that try to illustrate this, but the point is that most of your robot software should be reusable. And in fact, the application-specific part of it, over time, we're hoping becomes a very, very small piece of the overall software, with the goal being that we increase the robustness and the stability of these systems and improve their testing over time. So I've also shown where the Gazebo project fits in, so that when you're developing the software, you can have this Gazebo simulator running, and you don't actually have to have a physical robot. That's great for lots of reasons. For example, this is a Turtlebot, which is a relatively low-cost robot, but even when I say that, you kind of have to have an asterisk, because a low-cost robot is still, odds are, $1,000 or more. So because of that, there's not an infinite supply of them in every lab. Even well-equipped labs might not have as many robots as there are engineers. That's typically true when you get into more exotic research platforms where they can easily cost $1 million or more. So being able to have a simulator that works, that you can target from your day-to-day work, is something that I'm sure many people here are familiar with in the embedded context, but it's just the same for robots. With the added constraints that robots break, they have batteries that discharge over time, and unfortunately those batteries usually discharge as it's running down a corridor away from you, and then it gets stuck in a corner where there's no Wi-Fi. So this type of thing happens a lot, and being able to have a simulator can simplify and just make the daily life of coding easier. But what we're trying to do with ROS is make it so that the software interfaces and all the interconnections that are happening on the network look the same, whether it's the simulator, or in fact now you can plug in a real Turtlebot there with a Dragon board on top of it. But your software should be qualitatively the same. And the parameter tuning and such, we're trying to abstract those away into text files so that the vast majority of the software runs the same, whether it's in simulation or in the real hardware. So I'd like to then show a video of a Turtlebot running around with a Dragon board 410C on top of it. So if we could play the video, it's called TB2E. This video was made by the good folks over at Make Magazine. They posted it on YouTube, so there's a full video you can see on YouTube that includes interviews they've done with others. But that's a Turtlebot, a small little robot there with a Dragon board on top. it has a depth camera on the Turtlebot. It's looking at the person in front of them, and then as that person speeds up or slows down, the Turtlebot then speeds up or slows down to follow right behind you. And it's a fun demo for trade shows, but it actually has economic implications because if we can roll it again while I keep talking over it, that'd be great. What you can do with this is a warehouse picking application, for example. Rather than walking down the warehouse shelves with a cart or some other way to carry the items back, you can have a robot that follows behind you with a big box on top. And then this application actually runs today. People use ROS to do this exact application for warehouse picking, where you're rocking down these big, huge warehouse floors, picking things out of boxes and putting them in the robot. And then when you're done with the order, you can tell a robot to go back to the shipping department while you keep picking more orders and a new robot comes to follow you. So again, we did this demo at Maker Faire this last year using the Dragon Board 410C on top. And if I could go back to the slides now, I'll skip ahead. Thank you. So if we look at the hardware that's happening here, we have the Dragon Board 410C, which is the center of this little robot. It has a depth camera that's plugged into it. In this case, we're using an Orbeck Astra, but there's now a pretty big equivalence class of depth cameras made by various vendors around the world. We then have a joystick so that we can turn the following mode on and off or override the following behavior and teleoperate it directly. And then at the other end of the screen, we're plugging in the Turtlebot into the USB ports. So all these things are hanging off the USB tree, and we're trying to then have a way to expose them in a way that is ideally reusable for the vast majority of the software. So now, if we stop looking at hardware and look at a logical description of what's happening, I won't get into the details of all of this, but you can see that there's various software bubbles that are taking information in, processing them in some sort, and then passing them on to other bubbles. And so we oftentimes in computer science talk about graph theory. So we call this a computation graph in ROS, where every bubble in that graph is a piece of software, it's a module. And those can either run as separate processes, or for speed and efficiency, we can put some of these nodes, we call them, in the same process to have fewer data thrashing around through the networking stack. So the idea is that the vast majority of this can be reused. And in fact, for this Turtlebot follower demonstration, only one, I've drawn it in green there, the only piece of software that's unique for the Turtlebot follower is the one that's actually looking for it takes an abstract point cloud in, finds a ball of points, and then it tries to either speed up or slow down. But all the other supporting infrastructure around that is recyclable for other applications. And in fact, it's used, many of those nodes there are used in many other robots of wildly varying proportions, which I'll show in the future. So in general, this ROS, we call it plumbing to have this dynamic computation graph. It can be, all these nodes can be inserted and removed on the fly. And that's, it's useful oftentimes, maybe you want to have the robot switch modes where the computation changes a lot. But what's really oftentimes from a day in, day out perspective is you can sit down at a workstation in front of a robot that's misbehaving somehow and then launch a whole suite of debugging tools which will attach to the running computation graph. And these processes may be running on many different computers. And particularly when you sit up with your laptop or you sit at a workstation near a robot cell, you're then adding another machine to this computational graph and attaching visualizers, data loggers, or any other method of debugging tools that you might be interested in. This is the type of thing that almost every ROS developer does on a day in, day out basis. So there are many drivers for common hardware. It's to the point now where if there's a commercially popular sensor, odds are someone somewhere in the world has released a ROS driver for it. So all the depth cameras, which have really produced a revolution in robotics in the past few years, all of the common ones, at least that I'm aware of, has a ROS driver for them, which means that when you write your software, you're no longer targeting a specific camera. Instead, you can receive just what we call ROS messages, which are abstract structures, which include just the points from the camera. So you no longer have to worry about the particular initialization or shutdown features from all the different depth cameras you can buy in the world. The same thing goes for laser scanners. There's many, many different ones. There's the big ones that spin on top of autonomous cars. There's much smaller ones intended for smaller warehousing or research robots. All those things look the same to ROS now. You can write abstract, high-level logic code, which just receives these abstract messages. And the same could go on for other classes of devices and hardware. There are many tools available in ROS. So the most popular one that we see people use is the ROS visualizer, or RViz. That includes a bunch of different components in it. It's highly configurable, and you can assemble all the different visualization widgets in panels and save those configurations. So no matter what the robot platform is or the application you're working on, you can generate a configuration of RViz and then save it so that you can speed up things in the future. The most common and perhaps most useful mode people use this in is actually a 6D representation of any data source in the ROS system. You can then plot it and visualize it and zoom in and zoom out and rotate as you need. A lot of robotics systems deal with spatial data, whether you're looking for objects in the world and you're wanting to plot the robot's hypotheses of where those objects are, or making maps of the world, or drawing path plans, or watching robots as they drive around. A lot of robotics software tends to be spatially oriented. And so being able to debug this in a live view with everything represented in the same spatial tree is a very useful thing. At the next level, up on the stack, we have capabilities, and these are collections of ROS nodes that are tested and used together. So there's lots of different ones, ranging from motion planning for very complicated arms, down to any number of other aerial applications. But this slide is just showing another one, which is the 2D navigation. So lots of environments, such as this room, it's relatively flat floor. There might be a few little bumps in the floor, but you can treat it as a 2D plane. And so if we wanted to have a robot drive up this aisle between all the seats, come up here and deliver an object, then go back out and go out the door again, you could use this 2D navigation stack off the shelf. If you're using it for a popular robot, there's probably already a configuration that is reasonable for it. If not, you can configure it for your own robot platform. So this was originally developed for that robot at the lower left on there called the PR2, which was by a Bay Area company called Willow Garage. Many of us have a history with. It was used for that, but we were careful during the writing and design to make it all parameterizable. So that PR2 robot was a very exotic, top of the line, $400,000 research platform. It has it spared no expense to have everything you could possibly want. So on every corner of that robot, there's a wheel that you can steer independently and drive independently, which means the robot can go sideways, it can go forwards and backwards, it can spin around in circles while it's doing any of those things. That's great, and you can configure the navigation stack to deal with robots like that, but you can also configure it to much lower cost robots that just have 2 wheels and can go essentially just spin in place or go forwards and backwards. All that stuff can be configured. You can even see some legged robots there used in various applications. So how do we do this? To make it more useful, you can, of course, always build everything from source. This is an open source project, but that can take a long time because these are pretty big pieces of software. So we run a pretty extensive build farm with a lot of automation behind it. I know this is a familiar concept to many people in this room, but this is a ton of work, to put it mildly. So we support 3 ROS distributions at any given time. And you can think of those like an Ubuntu distribution or a Debian distribution. It's a collection of packages that are versioned together and that we try to lock and prevent regressions from happening on previously released distributions while we work on the next upcoming one, which is where all the thrashing happens. So people can target a particular ROS distribution for their application. We release them on an annual basis, and then we keep rolling it forward with the build farm so that you can have binary installs for, we're currently building for 8 binary targets. That includes 32 and 64-bit x86, 32 and 64-bit ARM, ARM-HF, and a few others. So when you multiply that together times all the ROS packages that exist, that's about 40,000 build jobs right now on the farm that we're turning over. So one of the natural questions you ask is, how big is this thing? How many people are using it? And ironically, for an open source project, as I'm sure many understand here, it's actually a hard question to answer because we license ROS permissively. It's a BSD or Apache licensed project, and so no one has to get our permission or even tell us they're using it. And oftentimes, we only know about use cases after a product has been released and they say, oh, by the way, this is running ROS. So this is plotting 6 years worth of data on our best attempt to quantify the user community, which is a tracking cookie from Google on the wiki documentation. Now, granted, a lot of people don't use the tracking cookies, or they turn them off in their browser, or other people use mirrors of our wiki for geographic latency reasons in other parts of the world. So this shows that we're about at 100,000 unique users per month. Each user of the wiki tends to come about 4 or 5 times per month. So it's about 400 or 500,000 sessions per month that we see. But I think this is, it's safe to say it's a lower bound of the user community due to the mirroring and then people who don't do the tracking. So that's a ballpark of 100,000 or say 200,000. I don't know quite what the multiple should be to estimate it. But if we look at where everyone's coming from, the US is the top, but again, this is just of the US wiki server. But surprisingly, see a lot of other countries very close behind it, even if those countries have local mirrors of our wiki. So there's a ton of people coming from China and Germany, Japan. And then it's also kind of fun to then divide that by population of the country. And we see, amazingly enough, apparently 0.2% of the population of Singapore is a ROS user, which is amazing. So Other countries have very high numbers as well there. The code base size, so the ROS core, that's like the message passing framework, the serialization, deserialization, some scheduling stuff, the clients in various languages. That's about 100,000 lines of code. I know lines of code is a terrible metric of size, but it is at least a metric that we can talk about. But the desktop full, that's when we add in things like the visualizer, the data recording, playback. That gets us up to about 400,000 lines. But then the much bigger community, which is far larger than just our little group of 18 to 20 people, that's about 4 million lines of code right now in the universe that's publicly available and publicly released using our build automation tools. So there's much more code out there that people don't take the time to release or that's happening behind private firewalls. So there's a lot of people doing a lot of stuff in robotics. It's a fun time in the industry. In fact, all the commercial applications we're seeing now with ROS is very fun to see. So this is everything ranging from drones for delivery or security purposes to hotel delivery robots by a company called Savvy Oak. There's an inventory management robot there called Tally, which will drive up and down the big box stores and make sure stuff is where it's supposed to be and it's facing properly and all the things you have to do to keep a big box store looking nice. At least they can manage it and know where to send people to focus their efforts. Precision agriculture is a big thing nowadays as everyone becomes more and more interested in conserving water resources and minimizing fertilizer usage and other chemicals. This is a big area that we're seeing several companies use ROS-based solutions for this, as well as street mapping and in general autonomous driving research. We see lots of companies using ROS, maybe not perhaps in production, but at least in the R&D lab where it's much easier to tinker with things in these open ROS systems and try things out. So to illustrate a little bit more, maybe I'll close here with a video called this 8 Years of ROS. This is, periodically we have people submit their videos and we'll make a collage, which is, everyone loves to see their robot on YouTube, of course, right? So, so if we could play the ROS 8 Years video now. It's a bit overwhelming, it's kind of shock and awe because we tried to include as many people as possible. So there's actually 4 quadrants that we'll show here with every few seconds showing a new application. This will be everything from industrial applications to research on various fields of domains, government labs, all sorts of stuff. You can see this is all using a ROS-based open source system beneath it. There's some things happening on the water there, some things flying. There'll be even some stuff going on underwater. You can see also lots of smart manufacturing cells. Industrial automation is a very hot topic nowadays because all these new sensors we have from the depth cameras and other low-cost, fantastic sensors, you can combine those with these big open source packages which can do mapping and object identification and localization to really make manufacturing much more flexible. That's an exciting area we're seeing lots of people do great work in. So it's a bin picking application you can see there, as well as all sorts of skid steer. It's fun also that robots come in so many shapes and sizes to see everything from these very small, lightweight drones up to multi-ton off-road vehicles. Okay, well, if we can skip back to the slides now, that full video is available online on Vimeo, I believe. So we're doing lots of work in various aspects. I'll just briefly flip through one, which is a security application or enhancements that we're working on with ROS. As was mentioned in the previous presentation, security is a huge issue. Robot systems are no different from any other systems that you deploy, so you need to worry about security. And in fact, robots also bring many more issues to the front, just like IoT, but now you add actuation and all the things bad actors could do with that. So this, again, I'll emphasize that the ROS community is much larger than just our group, but this is just a project that our group is working on. I'm not trying to say this is representative of what everyone else is working on in the ROS community as a whole. But we're also pushing forward more Turtlebots. We have the Turtlebot there with the Dragonboard 410C on it. There'll be lots of announcements in 2 weeks at our annual developers conference of a next generation of Turtlebot that we're looking forward to, and I can assure you that ARM single board computers will have a role in that as well. So lots of people are using ARM. This is just a list of self-reported boards people have used with ROS in various capacities. I actually haven't even heard of some of these, but this is what people have put on the wiki page of saying that they're used. We've again been using the Dragonboard 410C a lot at the Open Source Robotics Foundation. We really like that platform. So if I talk about security just for a minute here, over the years we've evolved a relatively homegrown communications setup for ROS. So the dashed lines there show ephemeral XML RPC connections between these ROS nodes. and a thing we call the ROS core, which is essentially a name service. It's like just tells other nodes where to find each other on the network. Once they find out where they're located, then they connect peer-to-peer and have a binary blasting, just big, heavy messages if they need to. Unfortunately, with the presence of bad actors, we don't want to just have that be all open anymore. And so now we're starting to work on putting all that traffic using TLS tunnels. So we can use encryption and authentication that you get for free with all the great work of OpenSSL, which I know many people here are also contributing to and helping to port that to all the computers in the ARM universe as well. So we're tunneling this traffic through to try to make it so at least it's harder. You can't just quite come through the front door anymore. You've got to go around to the side or the window or use some other exploit. And for that, since we know that nodes will get owned at some point, the classic ROS system is totally open. So this grew out of academic R&D where you want to have total access to the system and be able to subscribe or publish any data through the graph. The problem is now if we just start deploying in the wild and we allow, it'll happen, right? I mean, the evildoers are going to find some way to get in one process. We don't want them to be able to take over the entire robot through one process. And so instead what we're starting to do now is to memorize the graphs, which means the particular topology of which nodes are running on what computers, who's connected to who, if you can publish or subscribe, or if you can call a service or execute a service, or which parameters you can read or write. We can run the robot in what's called a training mode, where you're recording what you expect to happen in a normal course of operation. And then when you deploy the robot, you enforce that to only be the possible outcomes. So if an evildoer takes over a particular node of their graph, you say that that evildoer now is not able to then take over the entire system. They can only do what they can reach from that single part in the golden graph. And then finally, using all the process level security work that's been happening in the Linux community lately through the AppArmor interface to say which particular parts of the network or file system we want to allow ROS nodes to do. So we're providing a set of AppArmor profiles to try to make that easier to do. So I think I'm just going to leave it at that. We could go on and talk about our next generation networking stuff. I'm happy to talk after, but I don't want to run over time too much here. So I appreciate the time, and I'm happy to talk afterwards if anyone might have specific questions. Thank you very much.
Okay. All right, so now we're going to take a group picture. Basically, we're going to file out through here outside. After the group picture, there'll be the break will be out there as well. And then after the break, come back in and we'll start our day, our sessions of the day. Thank you so much.
Ready to burn, so get those stakes.